Thanks very much for the introduction. It is my pleasure to be here. I have been a researcher in computer security at Carnegie Mellon University for over 15 years now. And I started out in more or less sort of traditional or mainstream computer security. And over the years, I've drifted a little bit in the direction of focusing on things that impact users directly. So I started out more on the formal method side, and at some point I started looking at, well, you know, it's all well and good that we can prove something about a system, but what actually happens when we start considering the users that who sit in front of that system too? And of course, recently, you know, I couldn't help but notice that all my students are super excited about AI and machine learning. So we do lots of things having to do with AI and machine learning in computer security, and then that overlaps with my part-time job as a director of Scilab's Cyber Autonomy Research Center. So Scilab is our academic center in security and privacy at Carnegie Mellon, and the Cyber Autonomy Research Center is basically a center that tries to foster research at the intersection of AI, machine learning, and computer security. So I actually have a slightly unfamiliar to me role in speaking here in front of you today, in that usually when I speak in an event like this, I talk about the cool things that our research, that we invented through our research, or the cool things that our research taught us that we can now build better systems. We have new insights. And today we decided that I would sort of be on the other side a little bit. You know, we know that there's lots of awesome things that happen at the intersection of AI and machine learning and all the data that we now have to use AI and machine learning on. Lots of awesome things having to do with, we can have new products, new services, we can make life more convenient, we can prolong life, or have better medical care. We can defend ourselves better from attackers in cyberspace and elsewhere. But my thesis in this talk is actually going to focus on some of the pitfalls of what happens in this awesome new space. Right? And the idea of focusing on the pitfalls is to perhaps give some advance warning. Right? So this is an awesome space, collection of tools and data and so on. That we all want to use to accomplish great things, but there are also maybe some things that we should be concerned about or worry about, or that should give us a second's pause, and we should think about how to address them. So these pitfalls, I'll have three examples of pitfalls that will be or challenges that are drawn from the research that I've done with my colleagues over the past couple of years. The first one will be about the risks of putting users in the Internet of Things driver's seat. So this will specifically be in the space of end-user programming. I'm curious, how many of you have heard the term end-user programming? A few. Okay. So end-user programming is this idea that we want to make it possible for even users who know no programming language, have no experience as programmers, to create new functionality, right? And we want to do this through interfaces where somehow you can assemble small recipes or tiny little programs that will give users the functionality they want, but without requiring them actually to learn a programming language or have any experience in programming. And it turns out that this is great because users can customize the various services that they use anyway in ways that the service itself wouldn't necessarily be able to do. But it also opens the door to some new concerns, and I'll talk about that. The second thing I'll talk about is the challenge of understanding users' privacy preferences in an Internet of Things world. So now, in this new era, we collect more data about people than ever before, and this enables many of the great advances in convenience and healthcare and so on. But it can also be challenging, and one of the reasons why it can be challenging is that in most circumstances, and sometimes because of law, sometimes to avoid surprising users, we need to seek users' consent. And in order to seek users' consent, when the context of the data collection is complicated, seeking their consent might also be pretty challenging. My final example will be in the space of looking at machine learning algorithms themselves, and in particular, looking at trying to understand to what extent they are fragile to attackers who might seek to take advantage of it. And this is particularly relevant not just as we are deploying machine learning widely in various critical circumstances like to pilot self-driving cars, but also because we increasingly use machine learning algorithms to defend ourselves in cyberspace and elsewhere. Right? And so it would be troublesome, to put it mildly, if attackers were able to find flaws in these machine learning algorithms deployed in such scenarios that they could then somehow use to twist the machine learning algorithms to do the wrong thing for us and the right thing from the attacker's standpoint. So let me just dive right into this first example of putting users into the Internet of Things driver's seat. And as I said, this is in the space of end-user programming. So a little bit of context here. As this Internet of Things era has arrived, it has increased risks in a couple of different ways. One is that we have given attackers an expanded attack surface that they can go after. Right? And so what we've seen on a few different occasions is that a type of Internet of Things device has a flaw that attackers can easily exploit. So, for example, there are these reports of attackers breaking into Wi-Fi connected cameras and spying on people in their bedrooms, or breaking into large sets of Internet of Things connected devices and using these as a launching pad for a distributed denial of service attack. In this particular case, against DNS servers. So this is when attackers take advantage of flaws, or clearly agree are flaws in the Internet of Things devices. But there are also situations where we increase risk not because of a flaw, but because of new features. So one example of that many of you are probably familiar with is Strava and Fitbit heat maps. So this was also in the public press in the last several months. Both Strava and Fitbit, which are these services that collect data about your exercise and health habits and present it to you in an interesting graphical way, they both have the feature that they will draw aggregate heat maps of where people like to exercise. Right? And these heat maps are not composed of individual traces; they are the aggregation of many people's traces, and so any individual is kind of anonymous in these traces. But it turns out that these traces, these aggregate traces, were being being published widely, publicly to everybody, and it turns out sometimes these traces were of depicted people's habits in confidential locations. For example, on military bases. It turned out that these heat maps showed the world where it was that soldiers in a particular military base like to exercise. So here, this is a situation where it's not that the new service had a bug that an attacker exploited. It's that the new service had a feature which had unexpected security or privacy side effects that were not ones that we would have wished for. So it's the second kind of thing that is relevant for this example. So the particular end-user programming paradigm or service that I'm going to talk about here is something called IFT, which stands for if this then that. And it's a service that allows people to write these simple if-then rules to connect the behavior of various Internet of Things devices and various either Internet of Things or online services that they might be using. Here's an example of a rule that you can write using this IFT service. It's that if your Fitbit logs 10,000 steps, then maybe you want to automatically post a tweet to this effect. Right? And people might choose to use this rule to motivate themselves to share their exercise progress with their friends. This is a pretty commonly used rule on this service. Another rule that people might use is that if they are detected to be close to their home, then they might want their Nest thermostat or their other smart thermostat to start heating or cooling their house. This is a rule that is a convenience thing. Now what we wanted to look at is, great, this is cool new functionality, it may be useful, maybe just cute, but we wanted to see, are there circumstances where it also has these undesirable side effects of the kind that I was talking about with the heat maps, and specifically ones that have to do with security and privacy. So before I get to that, let me talk about the terminology here a little bit. In this IFT service, one of these rules is called an applet, and the applet is composed of a trigger and an action. And the trigger is the event that causes the rule to fire, and the action is the event that is executed by the rule if the trigger event has been observed. So some examples of triggers are an email has been received in my Gmail inbox, or I've reached my daily step goal, or I've been tagged in a photo on Facebook. And actions are maybe I create a new status on Facebook, or post a new tweet, or I set my Nest thermostat to be heating or cooling my house to a specific temperature, and so on. And the cool thing here is that you can combine events from totally different services, right? You can combine an event that has to do with Facebook with an event that has to do with your thermostat, or an event that has to do with Twitter, which is where this convenience and customization comes in for users, why users want to use it. And it turns out that things can also go wrong when we write rules like this. So consider, for example, this rule that has to do with if I take a photo with my iPhone, then this photo gets automatically updated and made public on Twitter. So this is a rule that I might use if I'm traveling and I'm eager to share all the cool photos that I take with my friends. But it might have unexpected side effects, in the sense that, okay, somewhere during my travels, maybe I need to apply for a visa, and as a part of doing that, I take a picture of my passport, and suddenly my passport winds up being in a publicly available in a Flickr photo, which is probably not what I wanted to happen. So this is an example of a secrecy problem, in that one of these recipes can have the effect of leaking private information. Here's another example where the applet is that if I'm tagged in a photo, then that changes my Facebook status. And this is if I'm tagged in a photo by anybody. And the reason that I might want to do this is that maybe I'm going to an exciting party and I want to make sure that people know how much fun I'm having. And so whenever somebody tags me in a photo, I want this to show up in my Facebook status. If you actually look me up on Facebook, you'll see that this is definitely not me. I think I have one post per year or something like that. But this again is a popular recipe. It might, however, have the unintended side effect if I forget to disable this recipe. That I don't know. Maybe I take a day off from work, claiming that I'm not feeling so well, and then I go do something fun outside, and somebody takes a picture of me and tags me, and my boss finds out through my Facebook status that I seem not to be as sick as I claim, and this gets me into trouble. So this is an example of a possible integrity problem, in the sense that a particular functionality was triggered by a source that I didn't trust. In this particular case, I have in effect given the right to update my Facebook status to anybody who tags me in a photo, which might potentially be anybody on Facebook, certainly all of my friends on Facebook. So our goals here with this particular research project were to systematically analyze these IFT applets for potentially harmful side effects. And the way we went about this is that we categorized the secrecy and integrity level of each trigger and action event. And then we defined what are safe combinations of these levels of triggers and actions. And using this definition of what was safe and what was potentially unsafe, we analyzed the applets at scale. So let me talk briefly about how we define these secrecy levels to decide which applets were safe and which were unsafe. So here we kind of started out with the notion of, well, in computer security, people have used this classification of information can be public or confidential or secret or top secret and so on, right? And in this context, it's okay if information flows in one direction but not in the other direction. And we had this vague idea that maybe something like that applied to end-user programming as well, except the label top secret certainly didn't quite seem to make sense, and the label public maybe or maybe it didn't make sense. So we set out to develop our own set of labels that would make sense for this end-user programming service. The label private was one that easily came to mind. There are many devices that produce information that normally only we know. So I weigh myself on my smart scale. It tells me how much I weigh, but this is, at least at the source, this is information that only I know. So we called it private. Then we had this notion of information could be restricted by a physical context. So this is a situation where anybody in my house or anybody in a particular room in my house can look at my Nest thermostat and see what the temperature in the house is. Random people can't do it, but if somebody is already in the room in the house, then they can. So we call this a restricted physical context. There's a similar restricted online context in the sense that I might share something with my friends on Facebook or a subset of my friends on Facebook. So I'm sharing it with more than myself, but I'm not sharing it with the entire world. And then there are situations when some information is just public. There's a news article. Anybody could have read this news article. There's nothing private about the information in the news article after it's been published. Yeah. Yeah. Right. Right. Yeah. It's not truly private. Yeah. So when I say private, I kind of mean, that's a very good point, and this is a super rough categorization. In this case, when I say private, I say, by default, I can see it, and maybe the developers of the service or the maintainer of the service or something else, but no other end users can see it. Yes. Right. Absolutely. And we have more sophisticated models than this. They would take a couple of hours to talk about. But this is a great observation. Okay, so these four course labels formed our secrecy lattice and describe how we think it's okay for information to flow through recipes. So in particular, if a recipe pushes information, that is, if the trigger event of a recipe is more public than the action event of a recipe, then that seemed like there can't be a secrecy leak there. Versus if the trigger event is more private than the action event, then the recipe is potentially leaking information. So examples of recipes, according to this, that would potentially be leaking information are, one example I already gave, that if I take a photo with my iPhone to begin with, this is just my photo, but then I'm pushing it to Flickr and making it public. So this is a flow from a private context or potentially private context to a public context. Another example is that if after I complete an activity in Strava, I automatically post a tweet with images taken from that activity. Again, that's a situation where I'm taking information that to begin with only I and service developers and maintainers knew about, and now the whole world knows about, or at least a subset of my friends with whom I'm sharing online knows about. And we similarly went and defined integrity levels. The integrity levels that we wound up with sort of match the secrecy levels. There was a notion of a completely untrusted context. For example, there might be triggers that have to do with what's the new most popular post on Reddit, right, which is something that any number of people can influence, right, and I have no way of controlling who is able to influence which is the top post on Reddit. And then there are examples like in the I already had the restricted physical example. For instance, if somebody asks the trigger event has to do with the Alexa in my house being asked to do something. Anybody who was in my house could have potentially done that. And at the bottom we have this trusted notion of trusted integrity level, which is if only I could have done something. So here the kinds of flows, the kinds of recipes that are okay are sort of the inverse of what we looked at previously. So in particular, if a recipe takes trusted information and bases a decision on this trusted information, perhaps in a less trusted context, that's fine. But if the recipe relies on untrusted information to make a high trust decision, then that might potentially be a problem. So an example is that I gave earlier is that if I'm tagged in a Facebook photo, then change my Facebook status. This is an example of I am outsourcing the right to change my Facebook status, which is a trusted context, to all of my friends, which is a less trusted context because it involves more people. Or another even more extreme one is a commonly used rule is that if a new attachment arrives in my inbox, an email with a new attachment arrives in my inbox, then upload that file to OneDrive or some other online service. So this is a situation where anybody could have sent me this email. I have no control over who might have sent me an email with an attachment, and yet as a result of this input coming from potentially anybody, I cause something to be uploaded into my OneDrive account, which only I control. Right? So maybe this lets the entire world fill up my OneDrive account and use up my quota and then cause something to not work because of that, or maybe it lets people put malware in my OneDrive account. So, this is an integrity problem in that sense. So we use these lattices to detect potentially harmful applets in the set of applets that this IFT service published. They published about 200,000 applets. So this is, people could create their own applets, and then they could say, well, let other people reuse the applets that I've built. And there were about 20,000 unique ones among those 200,000. They had almost 900 different trigger events that they talked about, and almost 500 different action events that they could cause. And we labeled all of these triggers and actions with these labels that I talked about, and then ran queries to detect potential secrecy or privacy leaks. And the bottom line is, we found that almost half of the recipes in this data set, half of the unique recipes, were potentially in violation, that is, potentially either had a secrecy leak or an integrity problem. And if we look at the breakdown, about 33% of all recipes potentially had an integrity violation, and just over a quarter of all recipes were potential secrecy leaks. So we looked at what were the most common categories of secrecy and integrity leaks. When we looked at secrecy, the most common one was that you were taking some private information and then sharing it either with everybody in a particular physical space or everybody in a particular online space. And of course, often you were doing this on purpose, but also this has the potential to cause incidents like the accidental sharing of your passport that I talked about. And these two categories accounted for the majority of violations. In terms of integrity, the majority of violations, vast majority of violations, was accounted for by recipes that took something from an untrusted context and then caused a high integrity or trusted event to happen because of it. So this is an example like, just because somebody posts something public, now I change my wallpaper or change my status or cause my door to unlock or something like that, thereby basically giving the entire world or a large set of people the ability to influence my private or trusted context. So the main takeaways from this particular study is that in this particular end user programming service, almost half of the recipes that people have published were potentially unsafe, and they could cause a wide variety of harms. We actually did a categorization of the kinds of harms that they could cause, and these harms ranged from personal harms in the sense of embarrassment to physical harms in the sense of opening your home up to burglary or letting people know where you were physically located at a time where maybe it would be easy to mug you, as well as cyber-related harms in the sense of making it easier for malware to infect your devices. And in this particular case, it seemed like these security lattices, which are a very traditional, I guess, formal method that we've thought about in computer security for a long time, they seem very applicable to this modern context as well. So that was the pitfall, and maybe the advice about this pitfall is, well, when we are creating cool new functionality, we should really be mindful of whether users are being given enough information about how that functionality is to be used safely. So maybe first we should think about not just what is the function, what's the first use of the function of the new functionality that we imagine or that we strive for, but also are there ancillary uses of this functionality which might have unintended security and privacy problems, and then can we educate users, or can we provide users with tools such that they avoid these problems in practice when making use of new functionality. Okay, so I'll switch gears and dive into my second example. My second example of a challenge or pitfall has to do with understanding users' privacy preferences in an Internet of Things world. And this is really all about how often to enable cool new features, we typically need more data. We collect more and more data about users. We collect video, we collect audio. I have a device that measures my heart rate. I have a device that keeps track of where I'm going. It's easy to build sensors that will say, measure my skin temperature and therefore make guesses about whether I'm feeling anxious or calm. There are video analysis techniques which will take a look at my face and tell whether I am happy or depressed or angry or whatever. And there's awesome functionality that can be built on top of this for my benefit, for public benefit, and so on. But in many cases, this functionality is all premised on we have to collect a lot of this data. And when collecting data, both for now, particularly with the GDPR for legal reasons, but also just to avoid freaking users out, there are a few standard guidelines that need to be followed. Often, a common rule that needs to be followed is people need to be informed about data collection, and that they have to be given choices. Maybe choices like, oh, do you want to donate this data in exchange for which you'll get this cool functionality? Or if you don't want to donate the data, that's fine, but you won't get this functionality, or maybe you'll have to pay a monthly service fee or something like that. Maybe we even want to automate some of this in the sense that if there's a lot to tell people about, maybe we want to figure out, can we develop machine learning-based algorithms that will tell us what are the things that people care about, and we only tell them about the kinds of data collection they care about and not about the ones that they don't. So therein come the challenges. In this new Internet of Things world where we're collecting so many different types of information for so many different purposes, what are the things that, how do we effectively notify people that we're collecting a particular data? What kind of choices should we be giving them? Are we collecting so much data in so many contexts that if we told end users about all of it, we would all spend our lives answering questions from our phones about is it okay to collect this data for this purpose, that data for that purpose, right? We wouldn't get anything done in our lives. So really to allow this data collection while also not wasting all of the users' time in informing them or giving them choices, we need to better understand what are the things that really matter to users. Under what circumstances will we allow data collection? Under what circumstances are they really uncomfortable? Under what circumstances they want to be notified? And so we did a study in this space. It was a Vignette study. Vignette study is one where you sort of give users a hypothetical scenario and you ask them to role play, imagine themselves in a particular context, and then answer a couple of questions of how they would react in that context. And it's a kind of a methodology that's been shown to be pretty effective at eliciting very accurate reactions. In here, we asked people to imagine themselves in a variety of hypothetical Internet of Things data collection scenarios. Here's one. The items in red are the items that we varied between the scenarios. So here the scenario is you're at work. This building has cameras that are recording video of the entire building. This video is shared with law enforcement for the purpose of improving public safety. And after it's shared, it will never be deleted. And then we asked people a number of questions. We actually exposed them to 14 scenarios like this, and then we asked them questions about would they want to be notified about this kind of data collection? Are they comfortable with this kind of data collection? Would they allow it or deny it if they had the choice, and so on? And then, based on the results, we built these statistical models that related, that tried to explain which factors that we explored in the vignette, so these items in red, like the location or the data type or the purpose or the sharing context, how and whether these affected whether people wanted to be notified, whether they were comfortable and would allow data collection. So here's a brief sampling of results. When we look at preferences to be notified, if data is shared or is biometrics data that we're talking about, then those are factors that cause people to probably want to be notified about the data collection. If the data collection is for a purpose that people find beneficial, for a subjective definition of beneficial, then they're less worried about it and they don't necessarily feel like being notified. If they are, so just to try to understand when they're uncomfortable with data collection, it turned out that if the data collection takes place in a public location, or it's environmental data, so not specifically about me, but just about my context, even though it may be influenced by me, that was something they were more comfortable with. And they were less comfortable with data collection in more private settings like their home, or a collection of more personally identifiable data like biometric data. And interestingly, this doesn't necessarily match when people were willing to allow data collection. So They were most willing to allow data collection when it was for a beneficial purpose, and less likely to allow it if there was sharing with third parties involved. So now these are all factors that make people more or less likely to be comfortable or to allow data sharing. But the real question is there a collection of factors, or is this one factor that is the dominant one? Because if it is, then maybe we can just tell users about that one factor and not bother them with all the other details when we're telling them that a particular kind of data collection might take place. And it turns out, maybe that's the type of the data, maybe it's the location of the data collection, or its purpose, or how long the data is kept. But it turns out it's none of those. It turns out that it's really all in the interactions between the factors, and interactions between the factors in a very personal way. So examples are, in terms of notification, what matters a lot is the combination, or what matters much more than other things is the combination of what data type is it and whether users perceive that there's a benefit to this data collection. So, for example, if we're talking about collection of biometric data and people are not convinced that the purpose is beneficial, then they definitely want to be notified of this happening. In terms of comfort, it's that it's about the intersection between the type of the data and whether users believe this is already happening and are familiar with this scenario. So if we're talking about people being caught on video and this is happening and people believe this is happening today already, then it tends to be the case that they're used to it and they're comfortable. Which doesn't necessarily mean they will allow the data collection. For allowing data collection, it's about the intersection of the type of the data and the location. So, for example, biometric data being collected in commercial settings is something that people generally would prefer not to allow if given the choice. So the takeaways here, I sped through a bunch of sort of snippets of examples, but the real takeaway is we had kind of hoped to find out that here are the two main factors that maybe explain how people feel about data collection, what makes them comfortable and what makes them allow or want to deny data collection. But it turns out that there's no one factor, there are no two factors. It's actually a bunch of factors, and different users care differently about different factors. So and on top of that, some of the factors are subjective. So really, this is kind of a negative result, saying, well, yes, we understand that in order to do data collection of end user data, we often have to be open and transparent about users, but users seem to care about so many things when it comes to the data collection that we don't know of any way to be concisely open and transparent with them. So this is an ongoing challenge that really need to address. And it's a challenge where if you're building a particular service in a particular context, then you will need to figure out in that context how to solve the challenge, because there isn't a one-size-fits-all solution. Right. We also discovered in the course of this work that these predictive models that we built that try to relate demographic properties of users and properties of the data collection scenario to the likelihood of people being comfortable or people wanting to allow data collection. These models can help, but they're still not there yet. And what I mean by that is they can help in that maybe they're accurate 80% of the time for a particular setting or 90% of the time for a particular setting, but they're nowhere close to 99.9% of the time, which is what you might need if you want to completely automate the process. Okay, so that brings me to my third and last example, perhaps also the most fun one. And here is where I'll talk about the extent to which machine learning algorithms can be taken advantage of by adversaries. So machine learning is becoming ubiquitous. I don't think I need to argue this anymore. It's used for things like cancer diagnosis, predicting weather, driving cars, and for surveillance and access control purposes. Now, in many tasks, machine learning algorithms, as of a few years ago, started outperforming humans. And in this particular example, I'll talk about computer vision because it's computer vision. I can show pretty pictures, and that makes for more fun talk. But all the things I'm saying actually apply to other contexts where we use machine learning too. So one of the tasks where machine learning started outperforming humans is the task of recognizing objects in images. So this happened around 2014. Algorithms just started being better than humans in how accurately they would identify objects in images. So here, a deep neural network, which is a kind of machine learning algorithm, can recognize that the first image is an image of a lion with very high probability. The second one is an image of a race car with kind of medium probability. And the third one is the image of a traffic light, with very high probability. But around the same time that these algorithms started outperforming humans on tasks like this, researchers noticed that the algorithms also exhibited some kind of bizarre behaviors. In particular, although they would get better accuracy than humans on sort of real-world tasks, there were these scenarios where you could slightly tweak the input to the algorithm in such a way as to cause a pretty weird effect. So here, each of the images that you see are actually slightly modified from the versions you saw previously. It's so slightly that probably the images seem identical or close to identical. But these three images, when the same neural network looks at them, it'll decide that the first image is the image of a pelican, the second image is a speedboat, and the third one is a pair of jeans. And it'll be pretty sure that it's right. Okay? So this doesn't seem so great. And if we look at the difference between the original images and the modified images that were misclassified, they're pretty small. There are pretty small differences. This sort of black column shows the difference between the two, and you really have to sort of magnify the difference before you start seeing that there, in fact, isn't a difference. The other question? Yeah. So these were differences that were specific differences that were introduced in the sort of while the researchers were exploring how robust these algorithms were. Right? It's not at this point these aren't really. It's not really clear whether these are an attack yet. They are just a demonstration that, oh look, this is really bizarre. The algorithm is 99% accurate in most circumstances, but I can tweak an image and suddenly get the algorithm to do a completely wrong thing. So my group's work and our work with collaborators came in is we want to understand, under what context is this actually an attack? And it seemed like well, in order to be an attack, there needed to be a scenario where an attacker would actually be motivated to fool a machine learning algorithm like this. Very likely that scenario might have constraints that weren't explored in this example that I just showed you, in the sense that it's unclear whether an adversary would be able to tweak individual pixels in an image in a completely arbitrary way while seeking to fool a machine learning algorithm. So we wanted to understand, well, are there actual attack scenarios where an attacker can do something like this? And in those attack scenarios, so what are the actual constraints that the attacker is operating under? So one part of this, what are the constraints, that has to do with fooling the machine learning algorithm. But another part of the constraints has to do with making sure that the attack is still relevant. So, for example, if I put a paper bag over my head, I will likely fool a machine learning algorithm for face detection, but it's not a very interesting attack because everybody around me will notice that I have a paper bag on my head and I probably won't be able to pass through a security checkpoint, right? So that would not constitute, in our eyes, an interesting attack. So we specifically started out by looking at physically realizable attacks that fool face recognition algorithms, and mounting these attacks in a way that was inconspicuous to the observer. We wanted to see, is this possible? So more concretely, what we want to see, is it possible that we could 3D print a pair of glasses that somebody could wear such that that person would then get misrecognized by an algorithm as somebody else? And I'll just very briefly tell you about the process that we wound up using to demonstrate that, unfortunately, this was indeed possible. We started out by collecting a data set of eyeglasses, pictures of eyeglasses on the internet. And we used these pictures of eyeglasses to train an algorithm to just generate realistic-looking eyeglasses. And so we showed it many eyeglasses, trained a neural network to generate yet more eyeglasses that were kind of similar. And we trained another neural network to discriminate between eyeglasses that were actually seen on the internet and made-up eyeglasses. So one algorithm generates eyeglasses, the other one tries to guess whether the eyeglasses are fake or real. And then we get these two networks to to train each other more. So we get the generator to output a pair of eyeglasses. We see if the discriminator thinks these eyeglasses are fake or real. If the discriminator says that they are real but they're actually fake, then we tweak the discriminator to work better. If the generator produces a pair of eyeglasses that were guessed to be fake, then we tweak the generator to make them more realistic, or some notion of realistic. So these aren't adversarial eyeglasses yet. So to make them adversarial, what we do is we take this generator, and we start feeding its input, its output, these eyeglasses that it produces. We start playing that output against a face recognition algorithm. So in particular, we take a face recognition algorithm, which here is correctly recognizing Owen Wilson as Owen Wilson. And suppose we want Owen Wilson to be recognized as Russell Crowe. What we do is we start taking these eyeglasses, we start putting them on Owen Wilson's face, and seeing what the face recognition algorithm says. And now if the face recognition algorithm says that these eyeglasses made Owen Wilson a tiny bit more like Russell Crowe, then we reward the generator by tweaking the parameters of the generator to encourage it to make more eyeglasses like that. If the eyeglasses somehow made the Owen Wilson even less likely to be Russell Crowe, then we tweak the generator to punish it, to make it more likely that it will never create eyeglasses like that. And we kind of iteratively repeat this process until we get a generator that is producing eyeglasses that are both hopefully inconspicuous, reasonably inconspicuous, and when worn by Owen Wilson, fairly reliably cause Owen Wilson to be misclassified as Russell Crowe. And here's an example of that with my student wearing eyeglasses that cause him to be misrecognized. So, let's see. Well, okay, I guess in theory, this is a video of my student standing in front of a face recognition engine, which is recognizing him as himself. And then when he puts on a pair of glasses, you would have seen him get misrecognized as somebody else. So in particular, while wearing this pair of eyeglasses, he gets misrecognized as another student, Ariel, with high probability. And this other student, Ariel, as you can see, looks very different from Mahmoud. It is much cooler as a video. So what this showed is that yes, we could actually create an algorithm that, in a perhaps somewhat realistic attack scenario, say trying to log into a Windows machine as somebody else, or log into an iPhone as somebody else, so a place we're using face recognition for a security-related purpose. It's actually possible for an attacker, under the constraints of the scenario, namely the attacker can't manipulate the pixels of the image, but can change his own appearance in a controlled way. It's possible in that context to mount an attack that fools the machine learning algorithm. Now, I didn't say anything yet about, is this attack truly inconspicuous? And if you look at these eyeglasses, they don't exactly look super inconspicuous, right? But we did a study to try to see if sometimes we could produce inconspicuous eyeglasses. So in this study, we created a bunch of these attack eyeglasses, and then we gave a bunch of people the task of telling us, presenting them with a list of eyeglasses and asking them to tell us, for each of these eyeglasses, are these eyeglasses real or fake? And we showed them both real eyeglasses and these attack eyeglasses. And it turned out that these are the results for the real eyeglasses. The y-axis shows the fraction of time the eyeglasses were selected as real. So for actual real eyeglasses, on average, 60% of the time people thought they were real. For some of the real eyeglasses here on top, people thought they were always real, but some real eyeglasses, these at the bottom, they also weren't very plausibly real to people. Now, if we compare that to how real people found fake eyeglasses, right, we see that for fake eyeglasses, the actual 3D printed ones, on average, 40% of the time people found fake eyeglasses to look real. And if we focus on just the eyeglasses that were as real as the 50% most real eyeglasses, right? About 30% of attack eyeglasses in the digital setting, and about 10% of attack eyeglasses in the real 3D printed setting passed off as realistic as the top 50% of real eyeglasses. So it actually, even though on that picture of Mahmoud, maybe the glasses didn't seem particularly inconspicuous, this user study shows that, in fact, many of the attack eyeglasses are as inconspicuous as many real eyeglasses. So it does seem that in this kind of attack, not only is it possible to fool the algorithm under constraints of a real attack setting, but it's also possible to do so in a way which doesn't arouse a great amount of suspicion from people nearby. Right. Right. Yeah. So that's a great question, and in fact, it's over all of the work that we do when we uncover a particular problem, then we notify whoever we think is most appropriate to be notified. So this situation we actually did at some point try to get in touch with the TSA. Now, for the TSA, this isn't probably it's unclear. This probably isn't a serious risk right now, because these attacks are specific to a specific face recognition algorithms, and so the attack that works against one algorithm doesn't necessarily work against another. And in particular, they are most effective against these machine learning, black box machine learning algorithms, which are very attractive because they're so accurate, and we use them more and more. But that's the sort of the state of the art, and the state of deployed practice is still a little bit behind, which is behind in accuracy, but fortunately also ahead in robustness. So really, one of the lessons here is that these attacks are a practical threat against some deployments of machine learning that you can imagine. And so one of the things we should do as well, we should be skeptical of machine learning that seems to work like magic, and we should also be careful where we deploy it. And so far, I feel like a lot of the security critical deployments, we're thinking about it, right? In particular, in the case of, for example, self-driving cars, maybe we're doing it a little bit, but we haven't done it too much yet. So this is a note of caution that we should continue not doing it too much yet until we better understand the circumstances when these algorithms can be taken advantage of by attackers. And that's that actually brings me to my conclusion, which is just I wanted to explore. I wanted to tell you about some of these pitfalls or challenges in this space of the combination of machine learning and AI and Internet of Things and lots of data. We can do great things, but also there are things that we maybe need to watch out for. And I talked about 3 examples of things to watch out for.
Any questions for Dr. Bauer? Sure, that's fine. Thank you. Other questions? Very cool. Awesome presentation. Thank you, sir.
Thanks very much.